Hello student, in previous lecture I have discussed about the effect of adding of pole and adding of 0 in transfer function. So if we add pole or 0 in transfer function, then our transient response automatically change. Okay, so we have already seen how pole and 0 affect our transient response. Okay, so see, adding some zeros and poles to the original system to improve its dynamic performance, which is known as compensation. Some of the So in this lecture we have discussed some of the compensation schemes. Okay, so let's start our discussion. So see, an automatic control system is used to maintain its output within desirable limits by means of a control action. Any deviation of the output from the reference input is detected by an error detector. The error thus detected is used as an actuating signal for control action through a controller. The proportional control action and types of control action used for improving transient and steady state response of a control system are described here in this lecture. Okay, so first we discuss about proportional controller. So see, proportional controller is a compensator and its output is proportional to error ET. That means difference between reference and output of the system. The addition of this controller increases the steady state gain, and the steady state gain is inversely proportional to steady state error. Hence, increase in steady state gain decreases the steady state error. But it is not possible to increase the steady state gain. This steady state gain sometimes called proportional controller gain. Okay, if we use proportional controller, then this steady state gain sometimes called proportional controller gain. So, but it is not possible to increase the steady state gain beyond certain value. For the system above second order, the increase in steady state gain drives the system towards instability. So increase of K means steady state gain. So increase of K decreases the steady state error to some extent. But it is not possible to move the steady state error completely because the proportional controller output is a function of error ET. Let us see more details on this proportional controller. Okay, so see, a proportional controller has a proportional term alone. The output of a proportional controller is proportional to the error ET. That means the difference between set point and measured value. Okay, so the equation representing the proportional controller in time domain is mt equal to kc et, and in the Laplace domain is ms equal to, if we are applying Laplace transform, then this mt equal to ms and this ms equal to kc into es. Okay, from which the transfer function of the proportional controller is ks equal to ms divided by es, and this is equal to kc. Now we take a first order system. Okay. Let the transfer function of a first order process be gs, and this gs equal to k divided by tau s plus 1, and the transfer function of the proportional controller be kc. Okay. Now the forward path transfer function is given by kkc divided by ts plus 1, and the closed loop transfer function is given by ts equal to cs by rs, and this is equivalent to kkc divided by ts plus 1, and this whole divided by 1 plus kkc ts plus 1. So if we simplify this equation, then we will get kkc divided by ts plus 1 plus kkc. Okay. Now if we take common 1 by 1, if we take common 1 plus kkc, then our equation will be this. In this equation we take common 1 plus kkc, that's why we divide this equation. This equation means ts divided by 1 plus kkc. So our equation will be kkc divided by 1 plus kkc, and this whole divided by tau s divided by 1 plus kkc and plus 1. Okay. So here we write this equation will be in this manner. That means we write this equation kcl divided by tau cl s plus 1, where kcl is equal to kkc divided by 1 plus kkc, and tau cl is equal to tau divided by 1 plus kkc. These are the closed loop steady state gain and closed loop time constant respectively. That means kcl and tau cl are the closed loop steady state gain and closed loop time constant respectively. Okay. So from this equation we can note that an increase in kc, that means if we increase kc, then tcl decreases. Okay. And if tcl decreases, then speeds up the closed loop response. Okay. So from this equation we can say that an increase in kc decreases tau cl and speeds up the closed loop response. Okay. Now if we calculate the steady state error for unit step input, then our steady state error is ESS, and this is equal to limit s tends to 0 SRS divided by 1 plus GS into HS. So here our input is step, that's why R is equal to 1 by S. So if we put R is equal to 1 by S, then our equation will be this, that means 1 by 1 plus KKC. Okay. So see, from this equation we find that the steady state error decreases as Kc increases. That is the system output will not exactly match the desired set point. The difference between the set point and the system output is known as steady state error or offset. When Kc approaches infinity, the steady state error becomes 0. But that is practically not possible. Okay. So see, from this equation we can find that an increase in Kc speeds up the transient response and reduces steady state error of the system. For the first order and second order system, the roots of the closed loop system with proportional controller lies in the left half of the S-plane, irrespective of Kc, and the system is completely stable. Okay. But this is not the case for higher order system. Okay, as Kc increases, some of the roots of the characteristics equation may move towards right hand side of the S-plane and drive the system to instability. Okay. Now we will discuss another compensator, that is derivative error compensation. Okay, so see, a system is said to have derivative error compensation if the generation of its actuating signal depends on the rate of change of error signal. For the system shown in this figure, that means figure 2.28, see, the type of compensation is introduced by using an amplifier which provides an output signal containing two terms. One is proportional to derivative of the error signal and the other is proportional to the error signal. Okay. A device which produces an actuating signal proportional to error plus proportional to derivative of the error is known as proportional plus derivative controller. So this controller is proportional plus derivative controller, because here see one proportional, because here see, in this system the type of compensation in this system is introduced by using an amplifier which provides an output signal containing two terms. One is proportional to derivative of the error signal and the other one is proportional to the error signal. Okay. So see, a device which produces an actuating signal proportional to error plus proportional to the derivative of the error is known as proportional plus derivative controller. Okay. So let us consider for this system Gs equal to K by S into tau S plus 1. Okay. That Gs here, Cs is equal to, here this is Gs. This is Gs. Okay. So this Gs equal to K divided by S into tau S plus 1. Okay. So see, the closed loop transfer function of the system without compensator, that means in this transfer function this compensation technique are absence. Okay, so if these are absent, then the transfer function is Ts equal to K divided by Ts square plus S plus K. Okay. Now, if we divide this transfer function divided by tau, then our equation will be K by tau divided by S square plus 1 by tau into S plus K by tau. Okay. Now see, from this equation, that means equation number 2.156, we can write omega n, that means natural frequency is equal to root under K by T and damping ratio zeta equal to 1 by 2 root under K into T, tau. Okay. Now see, here I have cleared this. Now see, the closed loop transfer function of the system Cs by Rs can be obtained by using the block diagram reduction technique. That means in this case we consider the compensator scheme. That means here Kc and Kds are present. Okay, so if we consider this Kc and Kds, then our transfer function, closed loop transfer function will be like this. Okay, so here the complete transfer function. So our transfer function is Cs by Rs equal to Kc into Kds plus 1 into K divided by S into tau S plus 1 plus Kc K then into Kds plus 1. Okay, so this transfer function is considered with the compensation scheme. Okay, proportional plus derivative compensation scheme. If we consider the compensation scheme, then our transfer function is Cs by Rs equal to this, which I have given equation number 2.157. Okay, so here if we assume Kc equal to 1, then our equation will be this. If Kc equal to 1, then our equation will be Cs by Rs equal to K Kds plus K divided by tau S square plus K Kd plus 1 into S plus K. Okay, now after simplifying the equation, 2.158 equation will be like this, which I have given the equation number 2.159. Okay, so after simplifying the transfer function, now the transfer function is 1 by tau into K Kd S plus K, and this divided by S square plus K Kd plus 1 divided by tau into S plus K by T. Okay, now see, the characteristics equation of the derivative compensated system is S square plus K Kd plus 1 divided by tau into S plus K by tau equal to 0, because we know the denominator part of the transfer function is our characteristics equation. Okay, so the characteristics equation is this, and we know the characteristics equation is equal to 0. Okay, so see, we can note that the natural frequency omega n is equal to root under k by t, and this is not changed when compared to the uncompensated system. So if we see in uncompensated system, here this is our uncompensated system, and in our uncompensated system natural frequency is omega n root under k by t. And with considering compensator, the natural frequency is same, that is omega n equal to root under k by t. This is not changed this is not changed. Now we calculate the damping ratio. Okay, so if we calculate the damping ratio, then we can write 2 zeta omega n equal to k Kd plus 1 divided by tau. So after simplifying this equation, we can get our damping ratio zeta equal to half into 1 by root under k tau plus Kd into root under k by tau. Okay, so comparing the value of damping ratio in the equation 2.162 with the value of damping ratio of uncompensated system, we can find that the damping ratio increases by an amount Kd root under k by tau after compensation. That means damping ratio increase by an amount Kd root under k by t after compensation. Okay, therefore the settling time Ts equal to, we know the settling time Ts equal to 4 by zeta omega n decreases because see, after compensation our damping ratio increase. So if damping ratio increase, if zeta is increased, that means settling time Ts obviously decrease. Okay, so increase of zeta means damping ratio improves settling time, but inclusion of a zero in the system increases the overshoot of the system. Moreover, in practical system, noise may be amplified due to derivative error compensation. So to minimize this problem, one can use an approximate differentiator instead of an ideal differentiator. Okay, now this case we will see in the next lecture. Okay.